Tonight, we are going somewhere very far away. Not far across a map. Far across time. So far that the numbers involved stop feeling like numbers and start feeling like something else entirely. Something closer to a dream. Tonight, we are going back 230 million years. To a world so different from the one you know that the air itself would feel wrong on your skin. The sky would be a different color. The plants would smell of things that have no names in any human language. The ground would shake under the footsteps of creatures that no living person has ever seen. Tonight, we are going to spend time with the dinosaurs. Not just one moment in their story. Not just the famous ones, the ones on the posters and in the museums. Tonight, we are going to follow them through the entire sweep of their reign. 180 million years. From the very first small, uncertain steps of their earliest ancestors, all the way to the last quiet moments of their final age. 180 million years. If you enjoy listening to sleepy prehistoric dinosaur stories like this, subscribe. I post stories like this weekly. Let that number settle over you like a blanket as we begin. Before we meet the dinosaurs themselves, we need to understand the world they were born into. And to understand that world, we need to go back even further. Back to a time when the very concept of a dinosaur didn't exist yet. When the creatures that would eventually become the most successful land animals in Earth's history were nothing. Less than nothing. A footnote. A marginal group of small bipedal reptiles scratching a living in the margins of a world that belonged to others. To understand what the dinosaurs inherited, we first need to understand what the world looked like before they inherited it. 252 million years ago. That number is almost impossible to hold in the mind. Human civilization, all of it, from the first cities in Mesopotamia to the screen you might be watching this on right now, spans roughly 10,000 years. 252 million years is 25,000 times that length. It is so far back that the continents of the Earth were arranged in a completely different configuration. The Atlantic Ocean didn't exist yet. The Pacific was a different shape. North America, South America, Europe, Africa, Asia, Antarctica, Australia, all of them were still fused together into a single enormous land mass. Geologists call it Pangaea, from the Greek for all Earth. Picture it. One continent. One vast, unbroken body of land stretching from pole to pole. Surrounded on all sides by a single world-spanning ocean called the Panthalassic, which simply meant all seas. It is difficult to overstate how alien this arrangement would have looked from space. From orbit, Earth would have appeared as a blue-gray sphere with one enormous rust-colored mass sitting slightly off-center, like a bruise on an eye. On the surface, things were even stranger. The interior of Pangaea was a desert. Not a desert like the Sahara or the Gobi, though both of those would have seemed modest by comparison. The interior of Pangaea was a desert on a continental scale, stretching for thousands and thousands of miles in every direction from any coast. The reason was physics. When air masses move over oceans, they pick up moisture. When they come ashore, they deposit that moisture as rain. But moisture doesn't travel forever. The further inland you go, the drier the air becomes as it drops its cargo of water along the way. On a modern continent, this creates a gradient from wet coasts to drier interiors. On Pangaea, the gradient was extreme. By the time any air mass had traveled 1,000 miles inland, it carried almost no moisture at all. And since the interior of Pangaea was not 1,000 miles from the coast, it was 3, 4, sometimes 5,000 miles from any ocean. The interior was bone dry year after year, century after century, millennium after millennium. Temperatures in the interior swung wildly. Without large bodies of water to moderate the climate, summer days could reach temperatures that would kill most modern animals within hours. 120 degrees Fahrenheit. 130. In some regions possibly higher. And then once the sun went down, the thin dry air offered no insulation and temperatures would plunge. 60 degrees of temperature change between noon and midnight was not unusual. The landscape was red rock and sand, scoured by dust storms that could last for weeks, baked and blasted into a kind of geological silence. But here's the thing about life. It finds a way. Not in the interior of Pangaea. The interior was effectively dead, a vast Martian wasteland that nothing larger than a microbe called home. But around the edges of the supercontinent, along the coasts and in the narrow bands where moisture could reach, life had survived. Battered, simplified, reduced to a fraction of its former richness, but alive. Because before we arrive at 252 million years ago, something terrible had happened. Something so terrible that it stands alone in the entire history of complex life on Earth. 252 million years ago was the end of the Permian period and the beginning of something geologists call the Permian-Triassic extinction event. You may have heard it called by its more informal name. The Great Dying. The Great Dying. Even the name carries a weight that most names don't. What happened during the Great Dying was this. A massive volcanic system in what is now northern Russia began erupting on a scale that defies comprehension. These weren't ordinary volcanoes. They were what geologists call a large igneous province. A flood basalt eruption, where magma doesn't explode from a cone but pours out of cracks in the Earth's crust like blood from a wound, covering vast areas in layer after layer of molten rock. The Siberian Traps, as this geological feature is now known, eventually poured out enough lava to cover the entire surface of Earth under 10 meters of basalt. But the lava wasn't the real problem. With the lava came gases. Carbon dioxide, sulfur dioxide, hydrogen sulfide, methane, a toxic cocktail injected directly into the atmosphere in quantities that dwarfed anything modern industry has produced. The carbon dioxide warmed the planet. Global temperatures climbed 5 degrees, then 10, eventually reaching perhaps 15 to 20 degrees above the baseline. Equatorial regions became uninhabitable. The sulfur dioxide combined with water vapor to create acid rain that fell constantly for thousands of years, dissolving limestone, poisoning soils, killing forests. The oceans absorbed carbon dioxide and acidified, making it impossible for shellfish and corals to build their protective structures. The warming oceans lost their oxygen, creating vast dead zones where nothing could breathe. Hydrogen sulfide bubbled up from the dying seas, poisoning coastal ecosystems and adding yet another layer of catastrophe to a world already coming apart at every seam. The result was the worst mass extinction in the history of complex life. 96% of all marine species went extinct. Not declined, extinct. Gone forever. 70% of land vertebrates vanished. Even insects, those endlessly resilient creatures who have survived every other catastrophe the planet has ever thrown at them, suffered significant losses. The only extinction in Earth's history where insect diversity declined meaningfully. The ecological collapse was total. Food webs disintegrated. Predators starved when their prey went extinct. Herbivores died when their plants vanished. Decomposers were overwhelmed by the sheer tonnage of dead organic matter accumulating faster than anything could break it down. Fungal blooms appeared across the dying landscape. Some rock layers from this period are dominated almost entirely by fungal spores, a world where decay organisms briefly outnumbered the living. This is the world that our story begins in. Not at the height of the catastrophe, but in the long, difficult, fragile aftermath. The early Triassic period, beginning around 252 million years ago, was a world in recovery. The Siberian Traps had quieted. The worst of the atmospheric poisoning was fading. But what remained was a damaged, simplified, traumatized biosphere struggling to rebuild. The creatures that survived were tough. They had to be. But they were relatively few in number and relatively limited in diversity. There were small fish in the recovering seas. There were some amphibians, clinging to existence in the muddy shallows of rivers and lakes. There were a few lineages of reptiles, still figuring out how to occupy the ecological spaces left empty by everything that had died. And there were synapsids, the mammal-like reptiles that had been the dominant large land animals of the Permian. Most of their lineages were gone. But a few had survived and they were beginning slowly to recover their former diversity. The synapsids are worth pausing on because they matter to our story in more ways than one. Think of them not quite as mammals and not quite as reptiles, but as something in between. Their own branch on the tree of life, distinct from true reptiles and distinct from the later mammals who would eventually descend from their smaller relatives. The synapsids of the early Triassic came in many sizes and forms. There were stocky, barrel-bodied herbivores that browsed the tough vegetation growing near water sources. There were sleek predators with differentiated teeth, some for gripping, some for cutting, that suggests early stages of the more complex dental arrangements we associate with mammals. Some synapsids were quite large. Some were small. All of them were trying to rebuild something in the wreckage of the world they had inherited from the Great Dying. And then there were the archosaurs. The archosaurs, the ruling reptiles, were a different branch of the reptile family tree entirely. They had survived the Permian extinction too, though in small numbers. And in the Triassic, as the climate stabilized at its new warmer baseline, the archosaurs began to diversify with remarkable speed. They split into two main lineages. One lineage would eventually give rise to the crocodilians, the group that includes modern crocodiles and alligators. The other lineage would eventually give rise to the dinosaurs, the pterosaurs and the birds. In the early and middle Triassic, neither of these lineages was yet dominant. The world was still transitional, still recovering, still figuring itself out. The synapsids held on in some regions. Various groups of early archosaurs competed for territory and resources. Small reptiles of various kinds occupied different niches. Amphibians still ruled freshwater environments in many areas. The world was full of empty niches, all those ecological roles that had been vacated by the extinction, and various groups were racing through the slow gradual process of evolution to fill them. By roughly 245 million years ago, the archosaur branch that would eventually give rise to the dinosaurs had begun to take shape. These were the early ornithodorans, a lineage distinguished by several key anatomical features, including a more upright posture than most reptiles. While typical reptiles walked with their legs sprawled out to the sides of their bodies, the ornithodorans were moving toward a posture where the legs were positioned more directly beneath the body. This seems like a small change. It was not. It would eventually prove to be one of the most important anatomical innovations in the history of land vertebrates. But we're getting slightly ahead of ourselves. In the Middle Triassic, roughly 245 to 237 million years ago, the world that would become the dinosaurs' world was still in its preparatory phase. The large, dominant archosaurs of this period weren't dinosaurs. They were other groups, the Rauisuchians, massive predators, some of which reached lengths of 20 or even 30 feet, with skulls filled with serrated teeth and bodies built for power rather than speed. There were the Aetosaur, heavily armored herbivores that looked something like a crocodile that had been crossed with a tank, their bodies covered in bony plates, some reaching 15 feet in length. There were Phytosaurs, superficially similar to modern crocodiles in body plan, lurking in the rivers and lakes of Triassic Pangaea. These were the rulers of the Middle Triassic world. And against this backdrop, the earliest dinosaurs were beginning to appear. But they weren't rulers yet. They weren't even close. They were small. They were marginal. They were, in every meaningful sense, nobodies. The stage was set. The world was damaged, strange, and slowly healing. The dominant creatures were powerful and well-established. And somewhere in the shadows, in the scrublands and forests of Middle Triassic Pangaea, something new was beginning to stir. Rest easy as we go there now. Let the ancient world settle around you, warm and slow and vast. There is a canyon in northwestern Argentina called the Esquigualasto Valley. It is sometimes called the Valley of the Moon, and if you have ever seen photographs of it, you understand why. The landscape is gray and sculpted and deeply strange, eroded badlands of Triassic Age rock, carved by millions of years of wind and rain into rounded hills and narrow gullies that look like nothing so much as a moonscape. The colors are pale. The silence is enormous. The sky above is a deep and stunning blue. In the 1950s and 1960s, paleontologists working in this valley began pulling fossils from the gray rock that would change the way we understood the history of life on Earth. They found dinosaurs. Not large ones. Not the giants that would eventually define the group in the popular imagination. These were small, lightly built creatures, some no larger than a German shepherd, some smaller. Bipedal runners with long legs, grasping hands, and heads equipped with rows of small sharp teeth. But they were unmistakably, anatomically, dinosaurs. And they were old. Very old. Dating to roughly 231 million years ago, in the Middle Triassic, the earliest Triassic. The oldest dinosaurs discovered anywhere on Earth. The most famous of these early Argentinian dinosaurs was named Eoraptor lunensis, the dawn predator of the Valley of the Moon. A creature roughly the size of a house cat, built for speed, with a lightly constructed skeleton and small serrated teeth suggesting it fed primarily on insects, small lizards, and possibly small vertebrates it could chase down and overpower. Close your eyes and try to picture it. A small, quick creature moving through scrubby vegetation at the edge of a river valley. The sun is hot and direct. It always is in the Triassic. The air smells of dust and the faint organic scent of the plants growing near the water. The creature moves with a certain quick, jerky efficiency, head turning, eyes scanning, always alert. It is not large enough to be the apex predator of anything. It spends much of its time avoiding the larger things that might want to eat it. This is Eoraptor. This is where it begins. Around the same time and in the same deposits, paleontologists found Herosaurus, a slightly larger and more robustly built dinosaur, perhaps 10 to 13 feet long, with a heavier skull and more clearly predatory dentition. Herosaurus was a real hunter, capable of taking prey significantly smaller than itself and possibly competing for carcasses with the larger archosaurs of the period. It was not yet at the top of any food chain, but it was working its way up. In Africa, particularly in what is now Tanzania and Zimbabwe, other early dinosaurs were being found. Nisosaurus parringtoni, which may be even older than the Argentinian forms, potentially dating back as far as 243 million years ago, though the fossil material is fragmentary and its exact position in the dinosaur family tree remains debated. But whether or not Nyasasaurus was a true dinosaur or simply a very close relative, it represents the whisper of the lineage beginning to form. A signal in the rock that something new was entering the world. What made these creatures dinosaurs? What distinguished them from all the other small reptiles and protoarchosaurs running around in the Middle Triassic? Several things, all of them anatomical and all of them important. First and most significant was posture. Dinosaurs walked with their legs positioned directly beneath their bodies, in what paleontologists call an erect stance. This is the stance of mammals. It is your own stance when you stand up straight. Most modern reptiles, lizards, crocodilians, have a sprawling posture with their legs angled out to the side so that their bellies are relatively close to the ground. This sprawling posture works, but it is energetically expensive. Every step requires the animal to lift not just its own weight but to counteract the torque created by its legs pushing outward rather than directly downward. The erect posture of dinosaurs was more efficient. Legs pushing straight down underneath the body use energy more effectively. This meant dinosaurs could move faster, could sustain movement for longer, could cover more ground per unit of food consumed. In the resource-limited world of the Triassic, this was not a small advantage. Second was the skeleton itself. The earliest dinosaurs had relatively hollow bones, not hollow like a tube, but with air pockets and thin walls that reduced weight without sacrificing structural strength. This is a feature that birds, the direct descendants of theropod dinosaurs, have retained to this day. Hollow bones are lighter bones, and lighter bones mean a more efficient body, particularly for an animal that relies on speed and agility rather than armored bulk. Third was something about the respiratory system, though this is harder to read directly from fossils. Modern birds have a uniquely efficient respiratory system involving a series of air sacs that allow a continuous flow of fresh air through the lungs, as opposed to the tidal breathing of mammals, where air flows in and out of the same space. There is strong evidence that this system, or something very like it, was already present in the earliest dinosaurs. If so, it gave them a significant advantage in terms of sustained activity. They could breathe more efficiently, extract more oxygen per breath, and maintain higher activity levels than animals with less sophisticated respiratory systems. These advantages were real, but they weren't immediately decisive. In the Middle Triassic, the dinosaurs were still marginal. In any given ecosystem, they might have made up 5% of the animal life, perhaps less. The large Rauisuchians and the armored Aetosaur and the various other archosaurs and synapsids that shared the world with them were more numerous, more established, more dominant. The fossil sites of the Triassic tell this story clearly. At Esquigualasto in Argentina, the formation that contains Eoraptor and Herosaurus also contains abundant fossils of the rhynchosaurs, pig-sized herbivores with distinctive beaked skulls that were far more common than any dinosaur. The cynodonts, advanced synapsids that were the closest relatives of true mammals among the animals of the period, were present and diverse. Various other archosaurs filled out the ecosystem. Dinosaurs were there, but they were a supporting cast in someone else's story. This would not last. In another fossil site, this one in North America, in the Chinle Formation of the American Southwest, we find a slightly later picture of early dinosaur life. By around 220 million years ago, the first clearly North American dinosaurs were appearing, small forms, mostly carnivores or omnivores, moving through forests of cycads and early conifers in what is now Arizona and New Mexico. The landscape here in the Triassic was very different from the modern desert. It was a complex, vegetated environment, not lush by later standards, but alive with plant communities that supported diverse animal life. These early North American dinosaurs were small. They were fast. They were flexible in their diets. And they were beginning to spread. Across the late Triassic, between roughly 230 and 210 million years ago, dinosaurs were present on essentially every landmass that made up Pangaea. This global distribution, achieved within a relatively short geological time window, tells us something important about these animals. They were good at moving. They were good at surviving in new environments. They were generalists in the best sense, capable of finding food and shelter and surviving across a range of conditions that would have challenged more specialized creatures. But they were still not dominant. Not yet. To become dominant, they would need one more gift from a catastrophic world. They would need the rain. And then, when the rain was finally done with what it had to do, they would need something else. One more apocalypse, one more reset, one more clearing of the board by forces beyond any creature's control. The story of how dinosaurs came to rule the world is not a story of conquest. It is not a story of superiority. It is, in large part, a story of timing. of being the right kind of animal in the right kind of body at the exact moment when the world needed exactly what you had to offer. Let that thought settle over you gently as the ancient night deepens and the first small dinosaurs move through the Triassic dark, quick and watchful and full of possibility. 234 million years ago the sky opened up. We have already spoken of this event, the Carnian pluvial episode, in other stories told on this channel. But tonight we return to it, because we cannot fully understand the rise of the dinosaurs without understanding what the rain did to the world they were born into. Without understanding how 2 million years of relentless precipitation dismantled one order of life and prepared the ground for another. The cause was volcanic. Beneath what would eventually become the Pacific Northwest of North America, a massive geological structure called the Rangelia Large Igneous Province was erupting. Not in the explosive, cone-building way we associate with conventional volcanoes, but in the slow, inexorable way of flood basalt eruptions. Magma pushing up through cracks in the crust and pouring across the landscape in wave after wave, covering areas the size of modern countries in layer after layer of cooling rock. The eruptions weren't constant. They came in pulses, separated by periods of relative quiet. But each pulse injected enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere, and the cumulative effect over hundreds of thousands of years was transformative. Carbon dioxide is a greenhouse gas. It traps heat from the sun in the atmosphere, warming the planet. As the Rangelia eruptions pumped more and more CO2 into the air, global temperatures rose. And as temperatures rose, the oceans warmed. And as the oceans warmed, more water evaporated into the atmosphere. And more atmospheric moisture meant more clouds, more rain, more intense storm systems. The hydrological cycle, the vast engine by which water moves between ocean, atmosphere, and land, went into overdrive. The monsoons that had always swept in from the Panthalassic Ocean onto the coasts of Pangaea intensified beyond anything the world had experienced in 100 million years. They became what scientists call megamonsoons, continental-scale systems of atmospheric circulation that could dump what we would consider a year's worth of rainfall in a single month. And they didn't stay confined to the coasts anymore. Pushed by the intensity of the atmospheric pressure differentials created by the extreme warming, moisture was being driven deeper and deeper into the continental interior than it had reached in millions of years. The deserts began to drown. Imagine it with me. That vast, red, Martian interior of Pangaea. The landscape that had been dry for so long that even the memory of moisture was encoded only in ancient geological layers far below the surface. Now rain is falling on it. Not gently. Not gradually. In torrents. Flash floods tearing through dried canyons, carving new channels, moving megatons of sediment. Water pooling in every depression. Dry lake beds, baked hard as ceramic, shattering under the assault of sudden water. Dust storms replaced by actual storms, lightning splitting the sky over a landscape that had barely seen lightning in millions of years. The first rains would have been chaotic. The soil, deprived of vegetation for so long, had nothing to hold it in place. The water simply ran off, carrying the top layer of earth with it, turning rivers and streams into thick brown torrents of suspended sediment. The runoff would have reached the coasts and poured into the seas, muddying the coastal waters, choking the light that filtered down to the marine ecosystems below. But then something extraordinary happened. Seeds and spores that had been dormant, some of them dormant for an almost incomprehensible length of time, waiting in the soil for conditions that had not existed in millions of years, began to germinate. Ferns and primitive plants whose ancestors had known wet conditions and whose descendants had preserved the genetic memory of those conditions, suddenly finding themselves in exactly the environment they were designed for. Within a few thousand years, nothing in geological time, the interior of Pangaea was greening. Not tropical rainforest, at least not at first, but something. Vegetation spreading across landscapes that had been bare rock and wind-blown sand. Tree ferns pushing their fronds toward a sky that was now gray with clouds rather than burning blue. Early conifers taking root in newly saturated soils. And rivers everywhere, carving the landscape into something new, connecting the coastal regions to the interior for the first time in the planet's history. The consequences for the existing inhabitants of this world were severe. The large dominant archosaurs, the Rawasuchians and the Aetosaur and the various other groups that had ruled the land during the dry decades and centuries of the Middle Triassic, were built for that dry world. Their bodies were designed for it. Their behaviors were calibrated to it. Their nesting sites, their territory sizes, their feeding strategies, their reproductive timing, all of it had been shaped by millions of years of adaptation to a specific kind of world. A hot, seasonally dry world where water was precious and predictable. where you knew when the rains would come and when they would stop. Now the rains didn't stop. Territories flooded. Food sources vanished as plant communities were upended, the drought-adapted seed ferns and cycads that had fed the herbivores dying back under the assault of too much water, their place taken by new species that the existing herbivores didn't know how to eat. Nesting sites that had always been reliable, patches of dry, well-drained ground, now sat under inches or feet of standing water. Eggs drowned. Entire breeding seasons failed. And when breeding seasons fail year after year for thousands of years, populations decline toward extinction with a mathematical certainty that no individual animal can resist. The Rauisuchians went first. The fossil record is clear about this. In the rock layers of the Carnian, the geological stage that corresponds to this wet period, Rauisuchian fossils become increasingly rare. Their diversity drops. Their geographic range contracts. And then, by the end of the wet period, they are essentially gone. Not because any single catastrophe killed them, but because they were specialists in a world that had ceased to exist. The Aetosaur followed a similar trajectory. The Phytosaurs persisted somewhat longer, helped perhaps by their semi-aquatic lifestyle. Rivers and lakes were, after all, more abundant than ever. But they too were diminished, reduced, simplified. Into this vacuum stepped the dinosaurs. Here is the crucial thing to understand about the Carnian pluvial episode in the dinosaurs. It wasn't that the rain was friendly to dinosaurs in some direct, obvious way. The rain was disruptive and challenging for everyone. The difference was that the dinosaurs were already built for disruption. Their relatively small size, most early dinosaurs were still quite compact, nothing like the giants that would come later, meant they could survive in fragmented habitats. When one area flooded, they could walk to the next. When one food source disappeared, they were flexible enough to exploit another. Their upright posture became a meaningful advantage in waterlogged environments where moving through mud and shallow water was a daily necessity. Their efficient respiratory systems allowed them to maintain higher activity levels in the humid, cloud-covered conditions where cold-blooded animals dependent on sunlight for thermoregulation were sluggish. Their relatively high metabolisms, if, as some evidence suggests, early dinosaurs were at least partially warm-blooded, kept them active and capable even on overcast days when the temperature dropped. And their small size meant they could reproduce faster, adapt faster, fill new niches faster than the lumbering giants they were replacing. The fossil record from the period of and immediately following the Carnian pluvial episode tells a story that is almost startling in its clarity. Before the rain, dinosaurs represent a small fraction of any fossil assemblage. After it, their proportion has increased dramatically. New species appear in rapid succession. Body sizes begin to vary. The first hints of the ecological diversity that will eventually characterize the group, small fast predators, large slow herbivores, medium-sized generalists, begin to emerge. The reign lasted approximately 2 million years, from roughly 234 to 232 million years ago. When it finally stopped, when the Rangelia volcanic province exhausted its magmatic reserves and the greenhouse gas injection slowed and the atmosphere began to drift back toward cooler, drier conditions, the world it left behind was almost unrecognizable compared to the world that had entered it. The Rauisuchians were effectively gone. The Aetosaur were in serious decline. The various other archosaur groups that had dominated the Middle Triassic were reduced to shadows of their former selves. The dominant synapsids, those mammal-like creatures that had been recovering their former diversity in the early Triassic, had been set back again. And the dinosaurs? They were everywhere. The 2 million years of reign had not made them dominant by itself. But it had cleared the board. It had removed the obstacles. It had created a world full of empty niches, simplified ecosystems with plenty of resources and few established competitors. And into that world, the dinosaurs were diversifying at a pace that was, by evolutionary standards, almost explosive. By around 225 million years ago, the late Triassic, dinosaurs had spread across virtually all of Pangaea. They were on every major landmass. They had begun to differentiate into distinct ecological roles. Some were becoming larger, moving into the apex predator niches vacated by the Rauisuchians. Others were developing the capacity for bulk herbivory, processing the abundant vegetation of the post-rain world. Some remained small and flexible, the nimble generalists who had always been the dinosaur default. The age was beginning. Not in a flash of triumph. Not with any conscious awareness on the part of these creatures of what they were becoming. But beginning nonetheless, quietly, steadily, one generation after another, as the dinosaurs filled the world that the rain had prepared for them. Let the image of that world come to you now, the new forests spreading across what had been desert, the rivers running full, the young dinosaurs moving through a landscape still wet and green from all those millions of years of rain. Feel the quiet of ancient times settling around you. By 220 million years ago, the late Triassic was well underway, and Pangaea was beginning its very slow disintegration. The forces of plate tectonics, the grinding, inexorable movement of crustal plates floating on the semi-molten mantle beneath, were beginning to pull the supercontinent apart. Rifts were forming in what would eventually become the Central Atlantic. The first narrow seaways were appearing between what would one day be North America and Africa. The changes were imperceptibly slow by any human standard. Continents move at roughly the speed of fingernail growth. But over millions of years, the geography of the world was slowly becoming less monolithic, more diverse. This gradual fragmentation had important consequences for the climate and, therefore, for the ecosystems that the dinosaurs were inhabiting. The interior of Pangaea, which had been warming and flooding during the Carnian pluvial episode, was now transitioning again. The great volcanic pulse that had driven the rain was over. The atmosphere was slowly returning to something more like its pre-rain state, though not identical. The rain had left its mark on the landscape in the form of new river systems, new lakes and richer soils in regions that had previously been desert. As the climate dried somewhat, the truly waterlogged conditions of the wet period gave way to something more seasonal, distinct wet seasons and dry seasons, with conditions varied enough across different regions of the vast continent to create genuine ecological diversity. The forests of the late Triassic were strange by our standards. There were no flowering plants. Flowers, with their extraordinary evolutionary partnership with insects and their revolution in seed dispersal, wouldn't appear for another 100 million years. There was no grass. The idea of a lawn or a meadow or a savanna was geologically impossible in this world. Instead, the vegetation was dominated by conifers, ancient relatives of the modern pine and spruce, growing in thick stands, their needles casting a diffuse shade over the forest floor. Between the conifers grew cycads, palm-like plants with stiff, feathery fronds and thick armored trunks. Ferns of all sizes carpeted the ground and the riverbanks. Horsetails, those primitive vascular plants that look like something from a science fiction illustration, grew densely in wet areas, some reaching heights of 20 or 30 feet. There were no songbirds in these forests. There were no flowering plants to attract pollinators. The air was not filled with the buzz of bees or the liquid calls of the birds we know. Instead, the dominant sounds were those of wind in the conifers, water in rivers and streams, the calls and movements of insects, which were abundant and diverse, and the various sounds of the reptiles that shared the world. It is worth taking a moment to simply inhabit this world. Imagine arriving there. Stepping out of whatever conveyance your imagination has provided and simply being present in a late Triassic forest, somewhere in what will one day be Europe or North America. The air is warm. Not uncomfortably so, perhaps in the range of a humid summer day in the modern subtropical regions. It smells of resin, of the sharp clean scent of the conifers, layered over a deeper earthy richness from the wet soil and decomposing plant matter of the forest floor. The ground under your feet is soft, a thick layer of fallen needles and decaying organic matter, rich and dark. Between the larger conifers, the ferns grow densely, their fronds unfurling in bright green spirals where light reaches the ground. Above you, the canopy is not complete. It is more open than a modern tropical rainforest, more like a mature temperate forest with gaps where the sky is visible. Through those gaps, the sun is strong and direct, though the latitude here is equatorial and the angle is steep. There is movement in the underbrush. Something small darts through the ferns and pauses, body low to the ground, head cocked in that characteristic quick-eyed attention of a small predator. It's a dinosaur, but not one you would immediately recognize as such. This is one of the small coelurosaurs, early theropods that were the dominant small carnivores of the late Triassic. Perhaps 6 inches at the hip, 2 or 3 feet long from snout to tail tip, built for speed, with large eyes for good vision in the filtered forest light. It watches you for a moment, then flicks away through the undergrowth with startling speed. A few hundred meters away, near a river, there is something larger. This is Plateosaurus. Or rather, this is one of the prosauropods, the evolutionary group to which Plateosaurus belonged, the first of the great herbivorous dinosaur lineages, the ancestors of the enormous long-necked sauropods that would dominate the Jurassic. In the late Triassic they were not yet enormous, but they were large. 20 to 30 feet long, with long necks already beginning to show the characteristic sauropod elongation, walking on 4 legs when browsing but capable of rearing up on their hind legs to reach vegetation higher in the canopy. Their bodies were built for processing large quantities of tough plant material. Their teeth were simple pegs, not sophisticated grinding structures. but their digestive systems were capacious, their guts long and efficient. Plateosaurus is one of the best-known early dinosaurs, partly because its fossils are remarkably abundant. In Germany and Switzerland and other parts of what was then the equatorial region of Pangaea, Plateosaurus fossils occur in such numbers that they suggest these animals were living in groups, perhaps small herds, and that when individuals died, they often died together, possibly at water holes that dried up during drought periods, trapping multiple animals at once. The prosauropods were significant for reasons beyond their own success. They were the beginning of an evolutionary trajectory that would lead, within a few tens of millions of years, to the sauropods, the largest animals ever to walk the earth. The elongated neck, the barrel body, the columnar legs, the small head perched on an impossibly long neck. All of these features were already nascent in the late Triassic prosauropods, waiting to be elaborated and amplified by the evolutionary processes of the Jurassic. The predators of the late Triassic were also becoming more impressive. Coelophysis is perhaps the best known of the early theropod predators, found in spectacular numbers at a site in New Mexico called Ghost Ranch, where hundreds of skeletons were preserved together in what appears to have been a mass death event of some kind, possibly a flash flood that caught a large group of these animals gathered at a drying water source. Coelophysis was roughly 9 to 10 feet long, lightly built, with hollow bones and a long narrow head filled with small serrated teeth. Fast, efficient, probably a pursuit predator that chased down small to medium-sized prey through open country. What is remarkable about Coelophysis, and what becomes clearer the more we study early theropods, is how modern they already were. Not modern in the superficial sense of resembling any living animal, but modern in the engineering sense, in the efficiency of the body plan, in the lightness and flexibility of the skeleton, in the sophisticated respiratory system that would eventually become the defining feature of birds. And birds, of course, are what the theropods were always moving toward, though they wouldn't know it for another 80 million years. The seas around the fragmenting Pangaea were rich with life. Marine reptiles were diversifying rapidly, filling the niches left empty by the great dying extinctions and exploiting the expanding shallow marine environments created by the new seaways opening between the fragments of the old supercontinent. Ichthyosaurs, those extraordinary dolphin-like reptiles that had independently evolved a fish-shaped body plan for efficient aquatic locomotion, were everywhere, some species growing to enormous size. There were nothosaurs and placodonts in the shallower waters. The first plesiosaurs were beginning to appear, those long-necked, four-flippered creatures that would become the signature marine predators of the Jurassic. In the rivers and lakes, early crocodilians were establishing themselves, though many of them were still quite different from their modern descendants. Smaller, more terrestrial, some even bipedal. The pterosaurs, those extraordinary flying reptiles that were the first vertebrates to achieve powered flight, were also present in the late Triassic, appearing in the fossil record during or just after the Carnian pluvial episode. The earliest pterosaurs were small, long-tailed creatures, probably insectivores or small fish eaters, fluttering through the Triassic skies with wings made of a membrane of skin and muscle stretched between elongated fourth fingers and their hind limbs. The world was becoming busy. Not yet as populated, as diverse, as ecologically complex as it would eventually become under dinosaur dominance, but increasingly alive. The empty niches left by the great dying were being filled, one by the survivors and their descendants. The dinosaurs were a major part of this filling, but they were not yet the overwhelming dominant force they would eventually become. For that, the world needed one more clearing event. One more catastrophe. One more volcanic winter that would take everything, shake it, and set it back down in a different configuration. This catastrophe was coming. And when it was over, the world would belong to the dinosaurs completely and utterly, for the next 165 million years. But not yet. Not tonight, not in this moment. In this moment, the late Triassic forest is quiet. The Plateosaurus herd browses the canopy by the river, their footfalls heavy but unhurried. The small theropods dart through the undergrowth. The pterosaurs spiral overhead on warm afternoon thermals. The world is strange and beautiful and very much alive. Let it be with you as you rest. 201 million years ago. The number has a specific weight to it in the study of prehistory. 201 million years ago marks one of the sharpest and most significant transitions in the entire geological record, the boundary between the Triassic period and the Jurassic period. And like most such boundaries in Earth's history, it was drawn in fire. The Triassic had been, for all its strangeness, a period of recovery and renewal. The world that had been nearly killed by the Great Dying had, over the course of 50 million years, rebuilt itself into something rich and diverse. The dinosaurs had found their footing. The prosauropods were browsing in forests across much of Pangaea. The early theropods were hunting in every suitable environment. The pterosaurs were filling the skies. The marine reptiles were flourishing in seas that were warm and productive. And the non-dinosaurian archosaurs, though diminished, were still present. The aetosaur had declined but hadn't yet completely vanished. Various other Triassic archosaur groups held on in some regions. Most significantly, the Crurotarsan archosaurs, the group that would eventually give rise to modern crocodilians, were still diverse and widespread, occupying both aquatic and terrestrial niches, competing directly with dinosaurs for some of the same ecological roles. And then, 201 million years ago, the Central Atlantic magmatic province erupted. The CAMP, as geologists abbreviate it, was one of the largest flood basalt eruption events in Earth's history. Associated with the very process that was beginning to tear Pangaea apart, the rifting that would eventually open the Atlantic Ocean, the CAMP produced enormous quantities of lava over a period of perhaps 500,000 years. The rock it left behind can still be found today in outcrops across eastern North America, northwestern Africa, and parts of Europe and South America. All these separate places were once close together, before the Atlantic opened between them, and the CAMP lavas covered all of them. Like the Siberian traps that had driven the Great Dying, the CAMP eruptions injected massive quantities of greenhouse gases into the atmosphere. But the CAMP events were episodic, pulses of intense activity separated by quieter intervals, and the climatic effects were therefore complex and varied. There were intervals of intense warming, followed by cooling, followed by warming again as different pulses of volcanic activity drove different climatic responses. What emerged from this climatic chaos was, from the perspective of existing ecosystems, catastrophic. The end Triassic extinction event wiped out roughly 34% of all marine genera, not as severe as the Great Dying, but still a major reorganization of marine life. On land, the effects were more dramatic in relative terms. The non-dinosaurian archosaurs were among the hardest hit. Aetosaur went extinct. The last of the Rauisuchians, already reduced and marginal from the effects of the Carnian pluvial episode, finally vanished entirely. The phytosaurs, which had been hanging on in freshwater environments, disappeared. The large procolophonid reptiles went extinct. Even some early dinosaur groups were affected, with several lineages not making it through the boundary. But the dinosaurs as a whole survived. More than survived. When the volcanic winter ended and the climate began to stabilize in the early Jurassic, the world that remained was one from which virtually all of the dinosaurs' significant competitors had been removed. The non-dinosaurian archosaurs were gone. The dominant synapsids had long since retreated to small nocturnal lifestyles. The ancestors of mammals, tucked away in burrows and tree holes, eating insects and small invertebrates, keeping out of sight. There were no large non-dinosaurian land vertebrates left anywhere on the planet. The world was empty. Or rather, the world was full of plants and insects and fish and amphibians and small mammals, but empty of large land vertebrates. Every ecological niche that a large land animal could occupy was vacant. Every forest browsing role, every apex predator role, every savanna grazer role, every ambush hunter role, all of them were open waiting to be filled. And the dinosaurs filled them all. The early Jurassic, roughly 200 to 175 million years ago, represents one of the most extraordinary periods of ecological diversification in the history of land life. The dinosaur family tree, already branching in the Triassic, exploded in the early Jurassic into an almost bewildering diversity of forms. The sauropodomorphs, the lineage of long-necked herbivores that had begun with the prosauropods, began producing the first of the true sauropods, massive quadrupedal giants that would eventually become the largest animals ever to walk the earth. The theropods diversified into large and small predators, filling niches from apex hunters to specialized small carnivores to insect-eating generalists. The ornithischians, the second great division of dinosaurs, characterized by their hip structure, began producing their own wide variety of herbivorous forms. All of this was happening on a Pangaea that was now actively fragmenting. As the Triassic gave way to the Jurassic, the process of continental breakup that had been barely beginning at the end of the Triassic was now clearly underway. The rift between what would become North America and Africa was widening. A shallow seaway was forming in what would eventually be the Atlantic. The Tethys Sea, already an ancient feature of the world's geography, was expanding. The single vast Panthalassic Ocean was slowly being replaced by a more complex arrangement of ocean basins. This geographic diversification had profound consequences for the dinosaurs. As the landmasses began to separate, populations of dinosaurs that had previously been in contact started to become isolated from each other. Isolated populations evolved differently. The geological accident of a seaway opening between two landmasses, cutting off gene flow between populations, is a powerful driver of speciation, the process by which one species becomes two. As Pangea fragmented over the course of the Jurassic and Cretaceous, the dinosaurs on different landmasses went their own separate evolutionary ways, producing the extraordinary diversity that would eventually characterize the group. But in the early Jurassic, this fragmentation was just beginning. The continents were still close enough that many species remained in contact across the rifts, or had recent enough common ancestors that they remained recognizably related. The dinosaurs of early Jurassic North America and early Jurassic Africa were different, but not impossibly different. They shared body plans and ecological strategies that revealed their common origin. Picture the morning light in an early Jurassic landscape. You are in what will one day be southern Africa, in the age when early Jurassic life was just getting organized, just beginning to fill the vast emptiness left by the end-Triassic extinction. The sun is rising over a landscape of ancient conifers and cycads, still wet with the night's condensation, the air carrying that particular early morning quality of coolness that will give way to warmth as the day progresses. In the distance, moving in a slow group through the open forest, you can see sauropods. Not the enormous ones. Not yet. These are early sauropods, perhaps 30 feet long, their necks not yet extended to the extraordinary lengths they will eventually achieve, their bodies still suggesting the prosauropod ancestors from which they descended. But they are unmistakably sauropods. The long neck, the small head, the barrel body, the columnar legs, the slow deliberate movement of large herbivores that have nothing much to fear. Watching them from a respectful distance, half concealed in the undergrowth, is a theropod. Lean, bipedal, perhaps 15 feet long, the early Jurassic predator studies the group with what might be described as professional attention. Not exactly patience. Dinosaurs, as far as we can determine, had no patience in the human sense, but something like the attentive alertness of a hunter waiting for the right opportunity. The world is very quiet, very large, very old, and completely, utterly given over to the dinosaurs. From this moment on, for the next 165 million years, the story of large land life on Earth is the story of the dinosaurs. Everything else, every mammal, every crocodilian, every large reptile, every amphibian, lived in the margins of a world whose center was occupied by these extraordinary creatures. Let that settle around you as the Jurassic morning grows light and warm. The inheritance was complete. 175 million years ago, the world was warming. The climate of the Jurassic, particularly the Middle and Late Jurassic, was significantly warmer than the world we know today. There were no polar ice caps. Sea levels were higher, inundating shallow continental margins to create vast inland seas and coastal habitats. The Tethys Sea, that ancient east-west waterway that separated the landmass of Laurasia in the north from Gondwana in the south, was wide and warm and extraordinarily productive. Carbon dioxide levels in the atmosphere were elevated compared to modern values, maintaining the warm greenhouse climate that the dinosaurs called home. Pangea's fragmentation was now well advanced. What had been one unbroken supercontinent was now, by the Middle Jurassic, a collection of larger and smaller landmasses still connected in some places but increasingly separated in others. Laurasia, the northern group comprising what would eventually become North America, Europe, and Asia, was still largely connected. Gondwana, the southern group, eventually to become South America, Africa, Antarctica, Australia, and India, was also still largely intact. But the seaway between them was widening, and the diversity of environments available across these landmasses was increasing. The forests of the Middle Jurassic were magnificent. In the regions that would one day become Morrison Formation of North America, one of the richest dinosaur fossil sites in the world, the landscape in the Middle to Late Jurassic was a mosaic of different environments. Seasonally dry open woodlands with groves of conifers and scattered cycads. Riverine corridors where the vegetation was denser and the canopy more complete. Floodplains of enormous extent, their soils regularly renewed by seasonal flooding that brought nutrient-rich sediment from upstream mountains. Upland areas with somewhat different plant communities than the lowlands. Across all of these environments moved the dinosaurs. And they had, by this point, become extraordinary. The sauropods. There is no way to write about the Jurassic without dwelling on the sauropods, because they were the defining ecological reality of the age. These were the long-necked, long-tailed, enormous-bodied dinosaurs. The ones that have fired the human imagination since fossils of them were first discovered in the 19th century. And they were real. Every image of a sauropod you have ever seen underestimates them somehow, because photographs and illustrations cannot fully communicate the sensory experience of being near something that large. Brachiosaurus was among the most impressive. Named for its distinctive body proportions, its front legs were longer than its back legs, giving it a giraffe-like upward slope to its body and allowing it to hold its head high above the trees. Brachiosaurus could reach heights of perhaps 40 or more feet. Its body was barrel-shaped and enormous, supported on 4 legs that were like living tree trunks. Its neck was long and graceful by any standard other than anatomical reason, sweeping up from massive shoulders to that small head with its distinctive rounded crest. The weight estimates for Brachiosaurus vary in the scientific literature, but the numbers consistently run into the tens of tons. 30 tons. 40 tons. Perhaps more. An animal of this mass, moving across the landscape, would have felt like a mobile geological feature. The ground vibration from a herd of sauropods would have been perceptible hundreds of meters away. And yet, watching the long neck sweep through the canopy of a Jurassic conifer stand, pulling down branches with that small but surprisingly powerful head, there would also have been something almost peaceful about it. The enormous scale creating a paradoxical sense of slowness and calm. The measured, deliberate movements of a creature so large that urgency had become largely irrelevant. Diplodocus was different in proportions but equally awe-inspiring. Where Brachiosaurus was tall and heavily built, Diplodocus was long, very long. Some estimates put its total length at nearly 90 feet, making it one of the longest animals ever to walk the earth. It carried its head lower than Brachiosaurus, possibly feeding at shrub and ground level rather than in the upper canopy. Its tail was extraordinarily long and tapered to a thin whip-like tip that some researchers have suggested could have been cracked like a whip to produce a loud sonic boom as a territorial or defensive display. Whether this was actually the case or not, the image is remarkable. A 90-foot animal whipping its tail through the Jurassic air and producing a sound like a gunshot. Apatosaurus. Camarasaurus. Brachiosaurus. Diplodocus. Supersaurus, one of the longest animals ever, possibly exceeding 100 feet in total length. The Jurassic Morrison Formation was home to a diversity of sauropod species that rivaled anything in the subsequent history of dinosaurs. How did they all coexist? The answer was in their feeding ecology. Each species specialized in slightly different parts of the available vegetation, different height ranges, different plant types, allowing multiple species to share the same landscape without competing directly for the same resources. The predators that shared this world with the giants were themselves extraordinary. Allosaurus was the apex predator of the late Jurassic North American ecosystem. Roughly 30 to 40 feet long, it was a large and powerful theropod with a distinctive skull, deep but narrow, with horns above the eyes, and jaws that could open extraordinarily wide. Recent research has suggested that Allosaurus may have hunted by using its jaws not like those of a mammalian predator that bites and holds, but more like a hatchet, striking downward with the upper jaw, inflicting deep cutting wounds rather than attempting to overpower prey with sheer biting force. How Allosaurus hunted sauropods is a question that has occupied paleontologists for generations. It is difficult to imagine a 30-foot predator taking on a 70 or 80-foot sauropod, and the size mismatch was certainly real. But evidence of Allosaurus tooth marks on sauropod bones tells us unambiguously that these predators were at least occasionally feeding on the giants, whether by active predation on vulnerable individuals or by scavenging. Younger, smaller, sick, or injured sauropods would have been the most vulnerable targets. The very old and the very young were probably the primary prey. There were other theropods in the Jurassic ecosystem too. Ceratosaurus, with its distinctive nose horn and keeled teeth, was a medium-sized predator that may have spent more time in or near water than Allosaurus. The megalosaurids, an early and diverse group of theropods, were present across Europe and Africa. Small coelurosaurs of various kinds occupied the smaller predator niches, preying on insects, lizards, small mammals, and early birds. The first birds. Archaeopteryx is the most famous, and it appeared in the late Jurassic of what is now Germany, in a time period of roughly 150 million years ago. It was, in its essential anatomy, a small theropod dinosaur, a maniraptoran, closely related to the dromaeosaurids, the raptor group. But it had feathers. Not protofeathers or protofilaments, but actual veined feathers structurally similar to the feathers of modern flying birds, arranged in wings capable of at least assisted gliding if not fully powered flight. Archaeopteryx was approximately the size of a raven. Its skeleton still showed the features of a theropod dinosaur. Teeth in the jaws, clawed fingers partway along the wing, a long bony tail rather than the abbreviated tail skeleton of modern birds. But it was a bird in any meaningful biological sense. And it was alive in the late Jurassic, fluttering through the forests and gliding over the lagoons of an ancient subtropical sea. It was the beginning of the most successful group of living dinosaurs. Because that is what birds are. They are not the descendants of dinosaurs or the relatives of dinosaurs. They are dinosaurs. The theropod lineage that gave rise to birds never went extinct. It transformed, refined, elaborated, and ultimately produced the approximately 10,000 species of living birds that share the world with us today. The dinosaurs did not die. Some of them just became very small and grew better feathers. But we are getting ahead of ourselves. In the Jurassic, the birds were just beginning. The world was theirs to explore. The skies above the conifer forests were crossed by pterosaurs of various sizes and by these first tentative bird-like creatures, testing the air with their feathered wings, working out the logistics of a new mode of existence. Beneath them, the great sauropods moved in their slow and mighty procession through the ancient trees. The world was full and warm and green. The rivers ran clear and deep. The teethous sea beyond the shore teemed with ichthyosaurs and plesiosaurs. The nights were filled with the movements of small mammals, creeping through the undergrowth in the dark hours when the great reptiles were less active. This was the Jurassic at its height. The planet Earth in one of its most extraordinary configurations, warm and rich and given over to giants. Let the image of those slow, enormous creatures rest at the edge of your awareness as your breathing slows. There is no hurry here. There never is in deep time. 145 million years ago, the Jurassic ended and the Cretaceous began. The transition between the two periods was not marked by any catastrophic extinction. There was no asteroid, no volcanic winter, no sudden clearing of the ecological board. The change was gradual, measured in the shifting frequencies of fossil species across a thick band of rock rather than in any sharp boundary layer. But something was changing. The world was reorganizing itself, slowly, in the particular way that worlds reorganize when the geological forces underlying them shift. The Cretaceous would last 79 million years, the longest of the three periods that make up the Mesozoic era. And it would be the richest, the most complex, the most ecologically spectacular of the dinosaur ages. The first and perhaps most fundamental reason for this richness was a biological revolution that had nothing to do with dinosaurs. The flowering plants. The angiosperms, the group of plants that produces flowers and enclosed seeds, appeared and began to diversify in the early Cretaceous. The first flowering plants were modest things, small herbaceous plants growing in disturbed habitats along riverbanks and forest edges. Nothing yet to suggest the 250,000-plus species that their descendants would eventually encompass. But they had something that no plant group before them had had: the capacity for extraordinarily intimate evolutionary partnerships with insects and other animals. Flowers are, at their core, a sophisticated communication and reward system. They offer nectar and pollen to insects, birds, and other animals. In return, those animals carry pollen from flower to flower, enabling fertilization across distances that wind-pollinated plants could never achieve. This partnership between flowers and their pollinators drove a coevolutionary explosion that changed every ecosystem it touched. The insects diversified in response to the flowers. New pollinator lineages evolved, new body forms, new behaviors. The plants diversified in response to their pollinators. New flower shapes, new nectar compositions, new strategies for attracting the right visitors and discouraging the wrong ones. By the middle of the Cretaceous, approximately 100 million years ago, flowering plants were beginning to dominate many of the world's vegetation communities, displacing or reducing the conifers, cycads, and ferns that had ruled plant life for the previous 200 million years. The dinosaurs noticed. Of course they noticed. When the food base changes, everything that depends on it has to change too. And the arrival and diversification of the angiosperms triggered a wave of dinosaur evolution that produced some of the most spectacular animals the world has ever seen. The ornithischian dinosaurs, the hip-structure-defined group that includes the horned dinosaurs, the armored dinosaurs, the plated dinosaurs, and the duck-billed dinosaurs, reached their peak of diversity and ecological dominance in the Cretaceous. And much of this diversification was tied, directly or indirectly, to the changing plant communities of the age. The hadrosaurs, sometimes called the duck-billed dinosaurs for their distinctive flat, toothless beaks, were perhaps the most ecologically successful herbivores of the late Cretaceous. They were large, often in the 20 to 40-foot range, and built for efficient processing of tough plant material. Their dental batteries were extraordinary, hundreds of tightly packed teeth forming a single grinding surface that was continuously replaced throughout the animal's life. As one tooth wore down, a new one moved up from below to take its place. The result was a biological grinding mill that could process enormous quantities of fibrous vegetation without ever losing its edge. Hadrosaurs were social animals, almost certainly moving in herds, and some of them produced their young in colonies. The famous good mother lizard, Maiasaura of Montana, is associated with fossil evidence of group nesting, with multiple nests in a single area and signs that adults return to care for hatchlings rather than simply abandoning the eggs. The discovery of this nesting behavior in the 1970s was one of the more significant shifts in our understanding of dinosaur biology. These were not the simple, instinct-driven creatures of earlier popular imagination. They were animals with complex behaviors, social bonds, and parental investment. The ceratopsians, the horned dinosaurs, were another spectacular Cretaceous success story. The group ranged from small, hornless, roughly dog-sized forms in the early Cretaceous to the enormous, elaborate-headed giants of the late Cretaceous. Triceratops, which most people know at least by name, was one of the largest, with a skull that could reach 8 feet in length, arguably the largest skull of any land animal ever. The frill, the 3 horns, the massive body, all of these features evolved over the course of the Cretaceous as the ceratopsians diversified and as the specific selective pressures of their ecosystems shaped their forms. What were the horns for? Defense against predators, certainly. The forward-pointing nasal horn and the 2 brow horns of Triceratops would have been formidable weapons against any predator that attempted a frontal assault. But there is also strong evidence for intraspecific use, fighting within the species, male-to-male competition for mates or territory. Fossil frills and horns show extensive scarring and healed injuries consistent with this kind of use. The elaborate headgear of the ceratopsians may have served as visual signals as much as weapons. Advertisements of fitness, displays of individual identity, the prehistoric equivalent of a peacock's tail. The ankylosaurs and stegosaurs, the armored and plated dinosaurs, represent yet another evolutionary experiment in the Cretaceous and earlier, herbivore niche. Where the hadrosaurs and ceratopsians responded to predation pressure by developing social behaviors and defensive weapons, the ankylosaurs went in a different direction. They became walking fortresses. The most advanced ankylosaurs of the late Cretaceous were covered from nose to tail in a mosaic of bony plates and knobs embedded directly in the skin, with a massive bony club at the end of the tail capable of delivering blows powerful enough to break bone. Dissection of modern crocodilian and tortoise specimens gives us some sense of how these defensive structures worked. They were not passive armor but active defensive weapons deployed with force. Against this backdrop of extraordinary herbivore diversity, the predators were also evolving. Tyrannosaurus rex. There is no way to discuss the Cretaceous without pausing here. Tyrannosaurus rex is arguably the most famous animal that has ever lived on this planet. Not the largest, not the most powerful by every metric, but the most iconic, the most studied, the most thoroughly embedded in human cultural consciousness. And it deserves its fame. Not because it was the biggest or the baddest, but because it was genuinely extraordinary. Tyrannosaurus rex lived in the very late Cretaceous, roughly 68 to 66 million years ago, in what is now Western North America. It was large. Fully grown adults reached lengths of around 40 feet and weights of perhaps 8 to 14 tons, depending on the specimen and the estimation method. Its skull was massive, designed not for the hatchet-style striking of Allosaurus but for pure crushing force. The bite force of Tyrannosaurus rex was the strongest of any non-aquatic predator in Earth's history. Those enormous banana-shaped teeth, serrated along both edges, were designed to pierce bone, to extract the marrow-rich interiors of large dinosaur skeletons. Its arms are famous for being small, and they were truly small, absurdly small by any comparison to its massive body. But recent research has suggested they were not useless. The muscle attachments on the arm bones of Tyrannosaurus rex indicate that those small arms were extremely powerful for their size, perhaps used to grip struggling prey in close quarters, or to help the animal push itself off the ground when rising from a prone position. What was Tyrannosaurus rex really like? This is a question that paleontologists have been wrestling with for over a century, and the answers keep changing as new discoveries are made and new analytical methods are applied to old specimens. We now know with a high degree of confidence that Tyrannosaurus rex had feathers, or at the very least, that its close relatives did, and that it almost certainly retained at least some feather-like integument, possibly on the head, neck, and parts of the body. The evidence comes from exceptionally preserved specimens of related tyrannosaurids from China, which show clear impressions of filamentous feather-like structures. We know that Tyrannosaurus rex had binocular vision. Its eyes faced forward, giving it overlapping fields of view in front, which is a characteristic of predators that need to accurately judge distances. The degree of binocular overlap in Tyrannosaurus rex was comparable to that of modern hawks. We know, from isotopic analysis of growth rings in its bones, that Tyrannosaurus rex grew rapidly during adolescence. Juvenile tyrannosaurids went through a growth spurt that added hundreds of pounds per year during their teenage years, before slowing down when they reached full adult size. We know, from the fossil record of its ecosystem, that Tyrannosaurus rex shared its world with extraordinary diversity of life. Triceratops was its most common large prey animal. Edmontosaurus, a hadrosaur, was another. Ankylosaurus, with its clubbed tail, was present and posed real defensive challenges. In the rivers and wetlands of the Hell Creek Formation, the specific ecosystem of the very late Cretaceous where Tyrannosaurus rex is found, there were also enormous turtles, large crocodilians, various lizards and snakes, and the small furry mammals that were everywhere in the shadows of the dinosaur world. The late Cretaceous was the culmination of 165 million years of dinosaur evolution. It was, in many ways, the most complex, the most ecologically rich, the most biologically diverse terrestrial world the Earth had ever seen. The diversity of dinosaur species in the late Cretaceous exceeded that of any earlier period. The ecosystems they inhabited were as complex as any modern ecosystem, perhaps more so. The behavioral sophistication of many late Cretaceous dinosaurs, evidenced by nesting behavior, social structures, elaborate display structures, and possible parental care, suggests animals that were, in their own way, as ecologically and behaviorally complex as many modern mammals. It was a world at its peak. And it was about to end. Let the richness of it settle around you as you rest. The warm forests and the vast open floodplains. The herds of hadrosaurs moving through the cycad groves. The tyrannosaurs moving at the edge of the treeline in the late afternoon light. The pterosaurs soaring overhead on wingspans that defied easy comprehension. This was the world. This was what 165 million years had built. 66 million years ago. Let's spend some time with this date. Let it become real. 66 million years ago, the Cretaceous period was still in full swing. The dinosaurs had been dominant for approximately 165 million years. Tyrannosaurus rex was alive. Triceratops was alive. The great hadrosaur herds were moving across the floodplains of western North America. The titanosaur sauropods were still browsing the forests of South America, Europe, and Africa. The skies were crossed by the last great pterosaurs, including Quetzalcoatlus northropi, with a wingspan of up to 36 feet, the largest flying animal ever to exist. The oceans were full. Late Cretaceous seas were warm and rich, filled with ammonites, giant mosasaurs, enormous bony fish, sharks, and the last of the great marine reptile dynasties. The continents were still not in their modern positions. India was an island continent drifting northward toward Asia, a collision that would eventually raise the Himalayas. Antarctica was warmer than it is today, forested rather than frozen. Australia was still closely associated with Antarctica. The Atlantic was still narrower than it is today. The world was, by any objective measure, thriving. Then, on a perfectly ordinary day in what geologists now call the Yucatan Peninsula of Mexico, a rock fell out of the sky. Not an ordinary rock. A rock approximately 10 to 12 kilometers in diameter, roughly the size of Mount Everest, traveling at something like 20 kilometers per second. The energy released on impact was approximately 1 billion times that of the atomic bomb dropped on Hiroshima. The Chicxulub crater left by the impact is 150 kilometers in diameter and 20 kilometers deep. It is perhaps the most significant single event in the history of complex life since the Great Dying, 186 million years earlier. Let's think about this slowly and gently because we are not trying to make it frightening. We are trying to understand it. To see it from the perspective of deep time, where even this extraordinary catastrophe is simply one more chapter in a very long story. The immediate effects of the Chicxulub impact were devastating at close range. Everything within several hundred kilometers of the impact site was killed instantly. The energy of the impact ejected enormous quantities of vaporized rock into the upper atmosphere, where it spread around the world within hours. Secondary impacts of ejected material caused widespread fires across the planet. The initial shockwave and the associated earthquakes and tsunamis would have been catastrophic for coastal ecosystems globally. But the medium-term effects were, in some ways, even more significant. All that ejected material in the upper atmosphere blocked sunlight. Not totally, not everywhere, but enough. Global temperatures dropped sharply. Plants, dependent on sunlight for photosynthesis, began to die. When plants died, the herbivores that depended on them began to die. When herbivores died, the carnivores that depended on them began to die. The food web, that intricate web of feeding relationships that structures every ecosystem on Earth, collapsed from the bottom up. The darkness lasted in its most intense phase, perhaps several years. Long enough to devastate plant life across the globe. Long enough to eliminate the productive base that supported the enormous biomass of the dinosaur world. The large dinosaurs, needing enormous quantities of food to sustain their bulk, were the first to feel the effects. The sauropods, which in the latest Cretaceous were still represented by several titanosaur lineages, required tons of vegetation daily. When that vegetation disappeared, they had no reserve. Within months, the great herds began to thin. Within years, the giants were gone. The smaller dinosaurs lasted longer, some of them perhaps much longer. The evidence from the fossil record suggests a complex, drawn-out extinction rather than an instantaneous one. Different groups disappeared at different rates. Some lineages may have persisted for thousands of years into the post-impact world, finding temporary refuges and habitats that retained some productivity. But eventually they all went. All except one lineage. The birds. The avian theropods, the direct descendants of small feathered Maniraptoran dinosaurs, survived. We don't know exactly why. Possibly their small size helped, allowing them to subsist on seeds and insects that persisted longer than larger food sources. Possibly their ability to fly allowed some populations to reach isolated refuges with more remaining productivity. Possibly it was simply luck. The particular combination of traits that characterized the birds happened to be compatible with the conditions of the post-impact world, while the traits of their non-avian cousins were not. But the birds survived. And from the roughly 20 or so bird lineages that made it through the extinction boundary, all 10,000 species of modern birds eventually descended. The non-avian dinosaurs, the sauropods, the theropods, the ceratopsians, the hadrosaurs, the ankylosaurs, all the vast and extraordinary diversity that had characterized the 165 million years of dinosaur dominance, were gone. Slowly, in the post-impact world, the darkness lifted. Not immediately. Not in any way that would have seemed like recovery to anything that might have been watching. The first years after the impact were cold and dark. The first decades saw the slow return of some plant life, the first tentative rebuilding of food webs. But it was a different world. Simpler. Quieter. A world still in shock. The forests that eventually grew back in the first few 100,000 years after the impact were strange forests, not the complex conifer and cycad communities of the Cretaceous, but simpler, opportunistic communities of fast-growing plants that could colonize disturbed ground. The fauna that moved through them was dramatically different from what had come before. The large dinosaurs were gone. The pterosaurs were gone. The marine reptiles, the mosasaurs, the plesiosaurs, were gone. The ammonites, those ancient and exquisitely diverse cephalopods, were gone. In the silence they left behind, another group began to stir. Small, furry, mostly nocturnal creatures that had been living in the shadows of the dinosaur world for 165 million years. Animals that had been kept small by competitive pressure from the dominant dinosaurs, limited to scrubby habitats and small prey because all the larger ecological roles were filled. Animals that had survived the impact, possibly because their small size and dietary flexibility allowed them to persist on the insect and seed resources of the post-impact world. Mammals. Our ancestors. But that is a different story. Tonight we are with the dinosaurs in their last hours. In the quiet of the late Cretaceous before the rock fell. In the warm, complex, richly inhabited world that had been building for 165 million years. Close your eyes and let yourself be there just for a moment. Stand in the fading light of a late Cretaceous afternoon. The Tyrannosaur is moving along the riverbank in the distance, its footfalls too slow and heavy to suggest anything other than patient, unhurried movement. A group of Triceratops is grazing on the far bank, their horns catching the low light. Overhead, a pterosaur glides in silence, riding the last thermals of the day. This world is ending. But it doesn't know it yet. It is simply alive, in the way it has been alive for 165 million years. Fully, completely, magnificently alive. There is a particular bird that I want you to think about. Not anything exotic. Not anything rare. Perhaps the most ordinary bird in the world depending on where you live. A crow or a raven or a common house sparrow, or a pigeon walking along a city street with that distinctive head-bobbing gait. Something small and feathered and unremarkable in the context of modern life. Because that bird is a dinosaur. Not metaphorically. Not in some poetic, loose sense. Literally, biologically, taxonomically, that bird is a dinosaur. It is a member of the lineage that includes Tyrannosaurus rex and Brachiosaurus and Stegosaurus and Triceratops. Its DNA carries the traces of 230 million years of dinosaur evolution. The hollow bones in its wings are the same hollow bones that Coelophysis ran on through the late Triassic forests of New Mexico. The air sacs that make its respiratory system so extraordinarily efficient are the same air sacs that Diplodocus used to process air in the warm Jurassic lowlands of what would become the American West. When you watch a bird, you are watching a dinosaur. This is not a small thing. 180 million years of dominance, a mass extinction that killed virtually everything else, 66 million more years of evolution and diversification, and here they still are. Roughly 10,000 species of them, living in every habitat on Earth from the Arctic to the tropics to the deep desert. Adapted to swimming, to diving, to soaring on thermals, to hovering in midair, to running along the ground, to digging burrows. The most successful group of land vertebrates on the planet by many measures. The dinosaurs never went extinct. They transformed. And this is perhaps the most important thing to take from the story of their 180 million years of dominance. Not the ending, which was dramatic in total for the non-avian forms, but the continuity. The unbroken thread that runs from the first small bipedal archosaur in the late Triassic of Argentina, through the giants of the Jurassic and the extraordinary diversity of the Cretaceous, and straight to the bird singing outside your window this morning. 180 million years. Let's think about this number one more time from a different angle. Modern humans, Homo sapiens, have existed for approximately 300,000 years. Our species, which has transformed the planet's surface, built cities, developed language and writing and mathematics and art and music and science and technology. Our species has existed for 300,000 years. The dinosaurs were dominant for 180 million years. That is 600 times longer than the entire existence of our species. It is the kind of comparison that makes the human story look, not small exactly, but very brief. A very bright flash in a very long, very dark night. What does it mean to be dominant for 180 million years? It means that every ecosystem on every landmass on Earth, for the entire duration of that period, was organized around the presence of dinosaurs. It means that every other animal that lived during those 180 million years, every mammal, every early bird, every lizard, every frog, every fish, lived in a world where large terrestrial ecological roles were occupied by dinosaurs. The mammals that were alive during the Jurassic were not the dominant animals. They were the mice in the walls. They were the creatures that scurried through the underbrush and hid in burrows and stayed out of sight of things that were large enough to eat them. The dinosaurs shaped the world those mammals lived in. They shaped the food webs, the vegetation patterns, the selective pressures that drove mammalian evolution. In a very real sense, the mammals that eventually gave rise to us were shaped, over 165 million years, by their coexistence with the dinosaurs. The very traits that define mammals, our warm blood, our complex social behaviors, our big brains, our nocturnal origins, our tendency toward parental investment in relatively few offspring, all of these may have been refined in part by millions of years of evolutionary pressure from a world dominated by dinosaurs. When the non-avian dinosaurs went extinct 66 million years ago, they left behind an immense ecological inheritance. Every large terrestrial ecological role, every niche for a big herbivore, every niche for an apex predator, every role in the food web that had been occupied by a dinosaur for 165 million years, suddenly became available. And the mammals, those small furry survivors of the apocalypse, were left to fill them. Within roughly 10 million years of the extinction, which is fast by evolutionary standards, the mammals had diversified into a remarkable range of ecological roles. Large herbivores were emerging. Apex predators were developing. Aquatic forms were returning to the sea. Gliders and flyers were exploring the air. The same ecological story that had played out at the beginning of the dinosaurs' reign, the ecological release following a mass extinction, the explosive diversification into empty niches, was playing out again, this time with mammals as the beneficiaries. And eventually, improbably, one lineage of those post-extinction mammals would give rise to creatures capable of looking back at the dinosaurs and trying to understand what their story meant. That lineage was ours. We are the inheritors of the inheritance. The dinosaurs dominated the world, and when they went, they left it to the mammals, and the mammals eventually produced us. Our existence is possible, in part, because of what the dinosaurs built and what their extinction made available. We are here because they were there. This is a strange and beautiful kind of connection. Across 66 million years of separation, 66 million years during which the planet continued to turn, the continents continued to drift, the climate continued to shift, and life continued to evolve in its patient, purposeful, direction-free way, across all of that distance, There is a thread connecting the first small theropods of the late Triassic to the birds in the trees and the people in the beds who fall asleep listening to stories about the deep past. One thread running unbroken through all of it. The fossils of the dinosaurs are themselves a kind of gift. They are the compressed remains of animals that were real, that breathed and moved and ate and fought and raised their young, and they preserve, in stone, evidence of a world that would otherwise be entirely beyond our reach. Every dinosaur fossil that has ever been found, from the most fragmentary isolated bone to the most spectacular articulated skeleton, is a small miracle of preservation. The odds against any organism's remains surviving 66 million years and being discoverable by curious primates with geological hammers are enormous. The fact that so many fossils have survived and been found is a reminder that the world keeps records, if you know how to read them. The study of dinosaurs has changed enormously over the past few decades, and it continues to change. New fossils are found every year, new species, new behaviors, new anatomical details that revise our understanding of how these animals lived and what they were capable of. CT scanners allow us to look inside bones without destroying them. Isotopic analysis lets us reconstruct ancient diets and growth rates and geographic movements. Trace fossils, footprints, skin impressions, nesting sites, give us windows into behaviors that bones alone cannot reveal. We know more about dinosaurs today than at any point in human history, and we know less than we will know in 50 years. This ongoing revelation is one of the most wonderful aspects of the study of prehistoric life. The story is never finished. There is always another fossil somewhere in the rock, waiting to be found, waiting to add another detail or correct another assumption or reveal something entirely unexpected about the world as it was. The dinosaurs are still teaching us things. They ruled the world for 180 million years, and even now, 66 million years after their non-avian representatives went extinct, they still have things to say. We just have to be patient enough and quiet enough to listen. Let the immensity of their story settle over you now like a warm weight. 180 million years. The Triassic forests and the early small hopefuls in the scrubland. The Jurassic giants moving through ancient trees. The Cretaceous world at its peak, teeming with horned and armored and feathered and enormous things. The last afternoon before the rock fell, when everything was still alive and full of its own ancient momentum. And then the silence, and then the small furry things beginning to stir, and then the long road back to a world that could eventually produce something capable of wondering about all of this. We are here. We are made in small but real ways, of what they were. That is not a small thing. That is, in its quiet way, everything. And so, here we are. At the end of 180 million years. At the end of a story so vast that no human mind can truly hold all of it at once. We can only move through it piece by piece the way you move through a great forest, one step at a time, one tree at a time, unable to see the whole thing from any single position inside it. You have traveled far tonight. You have walked through Triassic deserts and stood beside Jurassic rivers and watched the last Cretaceous afternoon fade into geological memory. You have kept company with creatures so large they shook the ground, and with creatures so small they hid in burrows and trembled in the dark, and with everything in between. The world is very old and very patient and very full of stories like this one, stories that the rocks hold in silence until someone comes along with the right questions to ask. Tonight you ask the right questions. Now let all of it drift away from the surface of your mind, like sediment settling slowly through deep water, layer by gentle layer, sinking toward the quiet dark at the bottom of a very old and very still lake. The dinosaurs are resting. The world is resting. Let yourself rest with them. Thank you so much for watching. If you'd like to see more videos like this, please consider leaving a like and subscribing to the channel, as it really helps us continue making more content. Anyways, see you in the next one. And now, close your eyes if they're not already closed. Let your breathing slow to the rhythm of deep time. Let the ancient world be with you in your dreams, the slow sweep of a sauropod's neck through morning mist, the footfall of something enormous on soft Jurassic ground, the call of the first birds rising into a sky that still remembers the creatures they came from. Sleep well. If you could spend one day anywhere in the 180 million years of dinosaur dominance, Triassic, Jurassic, or Cretaceous, where would you choose and what would you most want to see?